Okay, good morning, ladies and gentlemen. It is another Thursday, almost the end again, and we have with us Professor Charles Grant, who is the Director General for Iceland. Professor Grant got his master's in 1992, University of Surrey in the UK. As I said, he's the director at the Iceland. Last year, I believe, that he became professor, and we congratulate him for that accomplishment. He's had 2 decades of experience with operating and maintaining the Slowpoke research reactor. He is on part of many missions to Africa, Europe, Latin America, and the Caribbean. So he's very, very well and very well exposed in this area of nuclear science. Today, however, his presentation is in tribute to Professor Gerald Lalor, and the title of the presentation this morning is The Introduction of Nuclear Technology in the English-Speaking Caribbean, Its Impact on Development. And we thank Professor Grant for agreeing to speak with us this morning and to share with us on the life and work of the iconic Professor Gerald Lalor. Over to Professor Grant at this time. Thanking you again.
Thank you, Dr. Gallimore. So good morning, colleagues, friends, and students. So on behalf of the Department of Chemistry and Iceland, I would like to pay tribute to the late and great Professor Lalor, UE icon and institution builder. It is also very fitting that this tribute be given during this week as it coincides with the Nuclear Science Week. And as you will hear today, Prof. Lalor can be considered to be the father of nuclear technology in the region. I had the pleasure and honor of working with him, or knowing him for 28 years. I considered him a mentor and a friend, and I worked actively and fruitfully with him for 23 out of those 28 years. So with that said, I would like to say a little bit about the presentation overview. Can't start a tribute without mentioning his early years. I'd like to talk about his dreams. This is going to be very nuclear centric or Iceland centric, I should say, because that is really the forum in which I knew him. So I'll talk about his dreams and his vision and the history of the center, the first steps that were taken at the institution to make it what it is today, and its national and regional impact. I will talk about the present, what we're doing now, and his legacy, the future. So where do we start? Well, his long and distinguished career in chemistry, environmental research, geochemistry, and nuclear sciences was punctuated by many achievements, the first of which was the pioneering research on logwood dyes, for which he received his Master of Science degree from the University of London in 1957. The thesis was entitled A Physiochemical Study of Hemotoxylin, the Coloring Principles of Logwood. His research led to value-added output in medicine and industry, and also resulted in a full scholarship to pursue his PhD. Later on, 2 significant career-defining events took place in 1969. His receipt of the prestigious Carnegie Fellowship at Harvard University, and his appointment to the rank of professor, the latter a feat rarely attained by West Indians at the time. Professor Lalor quickly pivoted to the rigors and demands of the time and spaces he occupied during his meteoric rise within the UWI. This led to his appointment in 1969 as head of the Department of Chemistry, and then in 1972 appointed Pro-Vice Chancellor, and later in 1991 to principal. Now you can see Prof. Lalor's award-winning started at a very tender age of 9, as he achieved full scholarship for Kingston Scholarship, as shown in the newspaper article here. This is the younger Prof. Lalor in the 1950s during his MSc years at the University College of London. And this, very special to Iceland, this is the first sample ever to be sent into the reactor or house at Iceland right now. And Prof. Lalor being shown here. So as I said in the title of the presentation, a great institution builder. So these are 9 of the institutions that we know of that he built. These include the UWI Distance and Teaching Experiment, UEDITE, The Center for Nuclear Sciences later got transformed into Iceland. Postgraduate flats, now Gerald Lalor, the Biotechnology Center, the UWI Innovative Initiative Center and Science Park, the UWI Computing Services and UE Consulting and Analytical Services, Mona Information Systems Unit, now MITS, Mona Informatics, now Mona Geographic Information Systems, and the first supercomputer at UE, which placed us at the forefront of the digital age. As you can see, these are massive contributions to the university that still stand today. So, like I said, my presentation or my tribute will definitely be a Iceland's nuclear science slanted tribute to him and recognition of his work in this field. So how did it all come about? What was his dream? What was the epiphany? Well, during 1974, Prof. Lalor participated in an International Atomic Energy Agency, IAEA, sponsored tour of research reactors in the Soviet Union and East Germany, neither of which exist today if there are any younger members in the audience. It was there that he was introduced to the enormous potentials of geochemical mapping of surface soils. One such exercise in the Soviet Union led to the discovery of the world's largest deposits of tungsten. The analytical technique used was called neutron activation analysis. This, however, required an intense source of neutrons usually supplied by a research reactor. This convinced him that a geochemical map of Jamaica would be a good first step. All that was needed was a source of neutrons and a facility to house it. Now, impossible for most human beings, but I guess Prof. Lalor managed to pull it off somehow, quite remarkably, using European money to buy a Canadian reactor, which is completely unheard of, and I think even now is unheard of. So at the heart of this would be the Slowpoke 2 research reactor. So Prof envisioned an institution with a formidable range of applications that promised to impact Caribbean expertise and its potential to advance the application of science and technology to the sustainable development of the member countries of the UWI. As I said, at the root of all of this would be a Slowpoke reactor. As I said, the first limb being geochemistry that would branch out into all these other fields, all with a lofty goal for national development. As we can see, these are some of the areas that I will present on, or at least show you examples of later on in this presentation. So human health, medicine, clinical analysis, for instance, agriculture, food analysis, and so on. So what is a Slowpoke 2 reactor? Well, it's a 20 kilowatt reactor. It's a research reactor, of course, a tank in pool type design. The word Slowpoke stands for safe, low power, critical experiment. Now, please forgive the abuse of the C for a K, but it wouldn't look so nice otherwise. The reactor was designed by the Atomic Energy of Canada Limited, in particular by Dr. John Hilborn. The first Slowpoke went critical in 1970. This was upgraded in 1976 to a Slowpoke 2 at the University of Toronto. There were a total of 8 commissioned around, and only one outside of Canada, the one at Iceland. Yeah. Now, the Slowpoke at Iceland was the last to be commissioned with HEU, that is highly enriched uranium, essentially weapons grade material. That's no longer used for research reactors. We are the only nuclear research reactor in the English-speaking Caribbean, and as far as I understand, the only one on a small island developing state in the world. So it was commissioned in 1984 with 93% enriched uranium. Just to give you an example, a typical power reactor would be enriched from anywhere, well, from natural uranium, that was with 0.7% uranium and with heavy water moderated, to typically between 3 and 6% for a normal power reactor. But the expectations and uses are quite different. So just to give you an example of where 93% lines up with the world of reactors. The reactor to date now is operating with 20% enrichment uranium. So a HEU core that we had at the time consisted of 296 fuel pins. Shown here is the reactor fuel tank with the top off, with the reactor at low power, the light blue core shown at the bottom here. Like I said, we're located on a university campus. You already know that. So this is how it all began. In 1982, construction started. At that time, the fuel tank, which is an aluminum cylinder, was installed. At the heart of the reactor is what we call the critical assembly. The 296 pins that I mentioned earlier are housed in this aluminum cage. The total mass is about 1.2 kilograms. Ordinarily, that mass would not constitute a critical mass. That is, it should not be able to sustain a chain reaction. By surrounding it with beryllium, the excess neutrons that would ordinarily escape the body of the fuel are reflected back in, and hence the chain reaction can be sustained. Now, this is us today. I'm sure you've all passed the building. Shown at the bottom right is the reactor operating at full power. The light blue glow that you see is called Cherenkov radiation, and is caused by electrons, or beta particles as they are at the time, traveling faster than the speed of light in water. Well, not faster than the speed of light in a vacuum, but just in water. So I will share with you what the institutional vision was. Well, that was coalesced by the Committee on the Peaceful Uses of the Atom. It was a national group which is established with a wide representation to advise on all aspects of utilization and planning and project selection for the reactor. It worked so well that a number of the programs that were outlined then are still operational to this day. So what did it consist of? Well, you can all read the names below, but basically public sector, statutory bodies, and the scientific community, heavily influenced by the University of the West Indies. Our strategic plan and vision, I won't go into say too much about these, just to say that they exist and can be found. So what were the first steps? How we needed to become proficient in the technique that would provide the answers to our most pressing problems. The process that takes place, so our first issue was, how do we use this technique to understand what happens in the biosphere? So how do we go from understanding the fate of neutrons in a reactor during a chain reaction to understanding the fate of trace elements in the biosphere? So how does the environmental exposure affect human health? So the process that takes place in the nuclear reactor is called fission. Nuclear fission is a reaction in which the nucleus of the atom, in our case uranium-235, is struck by a slow-moving neutron, having been moderated in water, and then splits into two or more smaller nuclei, on average producing 3 neutrons per fission, as shown here. These in turn go on to produce 3 more fissions, and so on and so on. This chain of events is captured in the 6-factor formula shown here that we use to calculate how fast the chain reaction is going to move. Along with this is the production of a great deal of energy resulting from the transformation of mass into energy by the Einstein's famous equation E equals mc squared, where m is the mass deficit between the constituent particles and the actual mass of the element. There is a difference caused by binding energy, of course. You all being chemists know a great deal about this. So we are most interested in the excess neutrons produced by the chain reaction, not so much the heat and energy generated. So one technique to achieve everything, one technique to understand the biosphere was Prof's dream. So the discovery of nuclear activation was made in 1934 by Irene Joliot-Curie and Frederick Joliot, who bombarded aluminum, boron, and magnesium with alpha particles from naturally occurring radioactive material. Now, you may also recognize the Curie name, that she is, of course, the daughter of Madame Curie, double laureate for the discovery of radioactivity in 1903, and in 1911 for the discovery of the element polonium and radium. Now, it was first suggested in 1936 by Heberty and Levy that this methodology could be used as an analytical technique. So, like I said, Prof's vision was to have one technique that could do everything. Well, almost. So what are the basic principles of this technique? It's called neutron activation analysis, as I said. So samples are introduced into the flux created by the chain reaction in the core of the reactor. So I'll show you how we actually introduce a sample in a little while. There are several prompt reactions that take place. So this is the incident neutron, our target nucleus. So this is an element within the sample. A compound nucleus is formed. This decays or interacts almost immediately with the emission of prompt gamma rays and particles. We then go into what we call a metastable state. So the nucleus is still radioactive, but is not decaying immediately. Now, this is the beauty of the technique. This allows us then to move the sample from the reactor to our measurement device, to our photon detector. So what do we make of all this? Not every decay of an irradiated nuclei produces a gamma ray. It is a probabilistic event. So we need to understand what fraction of the total it represents. Now, please pay close attention to this formula as I'll be asking questions at the end. So what are we interested in? The detector response and how that relates to concentration. Like I said, the above is known as a single-shot neutron activation equation and is a basic equation used for the determination of elemental concentration in irradiated samples. So the physical constants never change. So shown here is the equation broken down into three distinct parts: physical constants, measured quantities, and experimental parameters. The physical constants never change. We just need to know them. The experimental parameters are calculated once and are extremely facility related, unique for each reactor and detector. Only 5 things to measure. These are quite simple. 3 are simple time measurements, shown here: the irradiation time, count time, decay time. 1 mass measurement, that is the mass of the irradiated element, and a peak area. Not complicated, right? So only these things to worry about. So as I said, this is how we introduce samples into the reactor. But they are dropped right in the beryllium annulus, the reflector that I showed you earlier, right beside the core, and are exposed to all the neutrons flying around here and here. Particularly for biological samples, they need to be very close to the reactor, as the concentration of elements in biological samples are quite low, so need quite a bit of activation. Geological samples can be put a little further away, based on the fact that their concentrations are quite high. So this is a typical detection system. I won't go into too much detail, but just to show this is the experimental setup. We have lead shielding, which surrounds our hyperpure germanium semiconductor detector. That shielding is both for the analyst as well as to keep the background radiation low on the sample, so we're not detecting cosmic radiation or the radiation from surrounding materials in the building. So this is what a typical setup looks like. It's not important for you to remember it, but just to show what takes place within our photon detector. But incident gamma rays generates a current in the detector. This is what happens here. So you see the various elements, different colors representing different elements. That leads to pulses being generated inside the semiconductor material. And the pulses are produced are proportional to the energy of the respective incoming gamma rays. So this is what we end up with. It's called a spectrum. Each one of the peaks in this spectrum represents a different element. The area beneath the peaks, which we gather by using peak deconvolution, directly relates to the concentration of the element within. So this is just a zoom of the previous spectrum that I've shown. And using software, we can actually determine the peak area beneath. So, bearing all that in mind, the single shot activation can be reduced to a few easily measured quantities. So the technique that we use is called the comparative technique. It's a comparator method, in which the unknown sample is co-irradiated with a comparator or a standard material, a material that we understand very well and know the exact concentration with. They are measured under identical conditions to the unknown sample. The main advantage of this procedure is that it eliminates the nuclear and instrumental parameters and simplifies the single shot activation equation, which relates to concentration in this manner, where C of the unknown is equal to the concentration of the standard over the mass of the standard over the mass of the unknown over the detector response corrected for time. It's just an exponential correction. So 3 years after the reactor had been commissioned, and with a great deal of training and equipment from the IEA, the institution hosted its first international training course on nuclear electronics. So we had arrived 3 years afterwards. It was such a monumental event at the time that the IEA actually commissioned a painting of the team then, Prof Lalor here, Mr. John Preston here, and Robin Rackery here, and Dr. Robotham here, commissioned a picture painting, sorry, and actually published it on their prestigious bulletin journal. So in the early days, this was our capabilities. This is where we are now. So you can see that, but we have made significant roads since the early days. And in fact, as I had said earlier, this almost does everything. We do in fact also utilize a number of complementary techniques at the institution, but this is not the discussion for today. So Iceland's priority areas, once we're up and running, as I said, Prof had a belief in environmental geochemistry as a first step. We then looked at how this impacted on agriculture and then on human health. In Prof's own words, I want to put Jamaica in a computer. So all this was stored in a computer readable database. So essentially we were looking at how rocks impacted on soils, how soils impacted on plants, and how plants impacted on human and animal health. The first sets of our first projects were, of course, geochemistry of soils, followed by heavy metal pollution in Jamaica, which essentially came out of the initial survey, which we identified several geochemical hotspots. In the following slides, I will share a snippet of the results of these studies. National and regional impact. So, like I said, the first thing was a geochemical atlas of the country. It provided baseline data on essential and potentially hazardous elements in the Jamaican environment. How did we do this? Well, we went across the island on an 8 by 8 kilometer squared grid, so at known distances, and took up to about 200 samples, I believe, across the entire island. Wherever we found hotspots, we went back in and did a more intense, higher resolution survey. So across the whole island, initially, we did 200 samples, but in Manchester alone, we did up to almost 600 samples. So what did this result in? Well, this is one of about 30 elements that we got from our analytical method, our NAA. So what you are looking at here is the alumina maps in the aluminium in soils across Jamaica. Naturally, this is perfectly overlaid with our bauxite mining. But what we also noticed is that there were a number of heavy metal pockets within the country. These largely also fell over the bauxitic area. So there's a very high correlation between the heavy metals and toxic metals with bauxite. So wherever we have high bauxite, we tend to find high heavy metals, in particular cadmium, which in itself is quite a problem as it's a known carcinogen. So we now knew what was in the soils. How does this affect agriculture? Well, naturally, we need to know where the farms were. So this is part of what we mapped. As you can see, with the assistance of the Ministry of Agriculture, we determined where farms were and their sizes and what they actually produced, and went in and sampled their produce there. One of the first things we looked at were tubers, of course. They're actually in the ground. And we sampled, and we could see where we took a yam sample, we took a soil sample, as you can see displayed here. Those in green represent soil samples below 10 ppm. Those in red were those above 10 ppm or micrograms per gram, now as it is now. But certain relationships were noticed, and we realized that the lower samples were found over the Cretaceous inlayers, so again, using the mapping, and those with higher concentrations of cadmium were found over the white limestones, typically found in our bauxite areas as well. So we also found a similar relationship with the yams, not unsurprising. And when we look at the actual numbers, as with all living things, uptake of elements is dependent on a number of factors. So no straight lines here. However, there is a distinct pattern we can see. As the soil cadmium increases, there is an increase in the tuber concentration. Naturally, like I said, there are a number of compounding factors. If you really wanted to know everything, you would have to account for rainfall and fertilizer use and so on. But even with that said, the pattern is clear, that you can see after a certain limit, you are going to exceed the safe index of cadmium in soil, in the tuber. We then went on, like I said, following the next logical step in the chain, which we look at animal studies. Was there a similar process taking place? And indeed it was so. Maybe not as strong because we had to correct for the age of the plant, but we actually measured the cadmium levels in bovine livers across the country, and a similar pattern was identified. Wherever it was high in the soil, it would be high in the livers of the animals. And again, environmental impact, again, how the environment will play into how humans are affected by all of this. So one of the first things that we always consider when looking at the environment is the air quality. So in Jamaica, the epiphytic plants or the genus Tillandsia were found to be widely distributed. We were looking for a cheap and abundant method of looking at air quality across the country. And Tillandsia was the plant that we found most abundantly across the country. And we found very high correlations of when we use our traditional active samplers with the Tillandsia. So it turned out to be quite representative of what was going on in the environment. So it turned out to be quite useful. Again, so eventually, how does this all play into health? What can we say? What can we see? Well, one of the first things we did, well, we utilized samples for 50 diabetic patients and 50 control patients, looking at how trace metals may impact on their well-being and so on. So in general, the mean and median values are generally higher in the control population. That means there was a depletion in chromium for diabetics. The difference between male diabetics in the control group and the control group was significant. A strong negative correlation for chromium with the age was observed. So the older you got, the lower your chromium got. We also looked at other trace metals. I mean, neutron activation analysis is very powerful, multi-element technique. We can identify up to anywhere between 30 and 50 elements, depending on the sample type. So the difference between diabetic populations for zinc was very distinct and is statistically significant. The test for HbA1c is a key indicator of diabetic control. For the male controls, there is a positive correlation for HbA1c and selenium, indicating that if you're normal, the higher selenium, the better your blood sugar control would be. The converse was true for diabetics, which is quite strange. We still haven't been able to find a reason for it, but it seems to be that the lower the selenium, the better your control was for diabetics. But we're still looking into what could cause that. We also took a look at human placentas to see how trace elements crosses the barriers and can potentially affect the fetus. Birth weight, which is, believe it or not, quite a strong indicator for how long you will actually live. We took a look at what elements affected that, and we noted quite strongly calcium to be quite strongly correlated with the birth weight of the child. The higher the calcium, the higher in the placenta, the higher the birth weight of the child. Also a slightly weaker correlation, but nonetheless there, with zinc. We also noted a strange phenomena with bromine and the age of the mother. However, we can't find any no natural use of bromine in the body. It turns up in a number of samples. We're not quite sure why that happened. We also took a very strong look at mercury. Now, the mercury levels in Jamaican placenta all fall below the level at which neurodevelopment problems become manifest. And so we were pleased to find that, because we also did a survey as to the amounts of fish that the mothers ate, fish being often a strong source of mercury. So we were pleased to find out that none of the persons that we actually measured exceeded the point at which brain damage would occur in the fetus. We've also done work for commerce and industry. Most notably was the construction of the pier in Falmouth, which was almost halted permanently due to elevated levels of cadmium nickel being reported in dredging samples. So this was part of the production process for the building of the pier. These levels exceeded the environmental limits in Norway. The Norwegian countries are very, very strict when it comes on to limits for the levels of heavy metals in the environment. They initially thought this was anthropogenic because they did the analysis independently of us. We were quickly informed that independent analysis provided showed these limits. We, Prof. Lalor and myself at the time, then produced a report based on our findings of our soil surveys across the country, showing that these sources of cadmium and nickel were actually naturally occurring. They are not anthropogenic. They were not caused by the dredging. And based on that, the project was restarted, a project that was valued at $224 million US. So our simple analysis helped to get that project back on target again, and our knowledge of our local environment. We were also involved in the cement quality control issue that some of you may remember. We were called on to recalibrate a number of their online testing systems that helped to quickly resolve the problems of the low quality cement on the market. Now, for those, just to give you a little refresher, Jamaica's cement crisis has thrown, or was at the time, an estimated 30,000 people out of work, and it's costing the country up to $100 million per day, according to estimates by the industry. So again, our simple analytical techniques, simple but accurate techniques, had helped to alleviate a problem in industry in Jamaica. Forensics. Now, some of you may remember this, but this actually happened. An entire beach was stolen. I think 500 truckloads. No one seemed to know where they went. This actually made international news. We were able to use elemental fingerprinting to discern the difference between potential recipient beaches and those that had not received sand from the stolen beach. So having the ability to analyze multiple elements at the same time, we can define a unique set of concentration ranges for each of the elements from different locations. You can confidently say that these sites, based on the range of elements, in this case, I think it's scandium, that they're from different locations. And using that, we were able to discern where the sand actually went, and beaches that had obviously nothing to do with the removal of the sand. So we also apply this technique, a slightly different data mining technique, to data that we gathered on 26 rice samples collected in Jamaica. We were looking at the nutritional value of rice being consumed locally in Jamaica, but we also thought it would be interesting to take a look at what the data could also glean. Using agglomerative hierarchical cluster analysis, which is a data mining method, we were able to discover 3 distinct clusters, and this was all done blindly. The samples were ground up and we put the data back together blindly. We were able to identify samples that were white rice, parboiled brown. We were even able to discern where the rice samples actually came from. They were elementally distinct. One of the more interesting points that we found was that we found a rice masquerading as brown rice that was actually, we believe, dyed. So it was an adulterated sample, brown rice selling at a higher price as it's supposed to be healthier. So just goes to show the power of the technique when done well. Now, we've kept relevant with relevant publications in areas of air quality, as I said, bauxite mining, looking at food quality, quantities, reactor physics, radon mapping, you name it. We've had numerous publications generated from our tiny little reactor. The university programs that we've been involved in, building our future leaders in local industry. These include physics, chemistry, geology, geography, botany, postgraduate programs in chemistry, botany, and geology as well. Research collaborations have been in geochemistry, physical chemistry, botany, again, you can see. So by having a broad cross-section originally from the CPUA, permitted diverse collaborations that were fruitful to all parties. So both locally, regionally, and globally in many disciplines, as you are seeing there. Now, we also thought it very important to remain having high impact locally. So a lot of the work that we did, we had publicized, or not just publicized, was covered by the local media. For instance, the lead poisoning issues that we had in Kintyre and in St. Catherine, we took care of and managed to lower the blood levels of children living on exposed areas. We're involved in the fertilizer scandal some years ago. And also Prof. Lalor headed a committee looking at the hyperglycine in an Aki study. Also looking at energy studies, or whether Jamaica would go, or whether it was possible for Jamaica ever to adopt nuclear power as a serious energy source. So we remained in the public eye, which we thought to be very important. So the present. Well, like I said, I had the pleasure of working day to day with Prof. Lalor from 1993 right up until his retirement in 2011. Then Dr. Richard Annells took over from 2011 until 2014, and then the baton handed over to me in 2014, so I've been director since then. Had quite an anonymous task to start off with. So in 2014, as a new Director General, I was tasked with changing the reactor core. So this formal request started back in 2001 by the University of West Indies via the IAEA, to basically the US government, to assist us in moving from high enriched uranium to low enriched uranium, with the spent fuel to be shipped back to the USA. Now, the removal of weapons grade material from civilian use was in line with Jamaica's firm commitment to the 3 pillars of the Non-Proliferation Treaty. That is nuclear disarmament, nuclear non-proliferation, and most importantly, what we do, peaceful uses of nuclear technology. And the removal was also in line with growing international consensus to eliminate the use of weapons grade material. So just to give you an idea of the complexity of this, so this plan was carried out over 3 countries, 1 international organization, and 35 ministries, agencies, and departments from the US government, Jamaican government, and the Canadian government. So it was quite a complex mission, but we managed. So just to show you here, so it started on August the 29th, and we finished up on the 4th of September. So 5-day pull down period. So this is the actual fuel being removed. What you are seeing here is the first set, the primary shielding, and this is the shipping container that the core, as tiny as it is, only 22 inches high by 22 inches wide. All this material was required to have it shielded to be shipped safely. So at 2:13 a.m., we finished loading the ship with the fuel, and this was the ship had left at 2:21 a.m. So that was the Caribbean removing its HEU. So what next? So how do we rebuild the reactor, basically? So this started on the 27th of September. This is the first fuel pin going in. So this is Prof. Lalor, one of the last times that he came around to Iceland, when we were actually doing our calculations for building the reactor up to critical. The reactor actually went critical for the first time, not at full load yet, on my birthday, September 30th, 2015, and was fully critical and ready for operation on October 6th, 2015. But the entire process took just over 10 days to complete. So this was the team back then, when we were young. So what's happening now, I'll just go through this really quickly. So one of the first things that we came across was we were approached by the Pan American Health Organization to aid investigations of possible arsenic poisoning and pollution of a small community in Grand Cayman. So just to show you, this is us at a news conference in the Cayman Islands. So samples were sent to us. These included soils, because you can see the concentration levels here, parts per million. And as you go down into pore water, micrograms per liter, and you go to micrograms per gram for local foods, and then your micrograms per gram again for fingernails. So what we did was, again, part of Professor Lalor's big dream, was to sample the biosphere. We looked at what was in the soil, what was in the water, what was in the food. And by looking at the fingernails of the groups, we could see what was in the persons. So at all stages, the control groups were always lower in general than the study area, particularly in the soil pore water, definitely in the foods, and definitely in the people. Now, I would just like to add, although the levels of arsenic in the study group or potentially exposed group was definitely higher than in the control group, they were not considered to be poisoned. So we could tell the difference, but it is a cautionary tale that they need to take these things into consideration. I won't go into too much details, but just to show you some of the research programs that we are still running using the same very powerful techniques 30 years on. So we're looking at the marine research. So looking at what's going on with corals, sediment, seagrass, and mangroves by collection of samples and then analysis. And I must add that all of these areas of research are generating publications as we speak. We have done elemental analysis of marine sediments. I'm looking at enrichment factors, geoaccumulation indexes, contamination factors, and so on. We have also assisted our governmental partners, NEPA, looking at cores presented in time series on how pollution is changing in the harbor. And importantly, microplastics. The Kingston Harbor was one of Jamaica's most polluted water bodies, but still remains as a key ecosystem for many marine birds and fish, and is also home to small artisanal fisheries. While many reports highlight the incidences of high levels of marine litter in Jamaica, the quantities of microplastic have never been evaluated. Although we have now published on this. Microplastics are becoming one of the more dominant marine pollutants worldwide and are documented to be detrimental to the survival of marine biota. Like I said, we try to remain relevant both in local newspapers and in peer-reviewed publications. So evidence has arisen of the negative impact of the presence of fish due to lionfish. Our solution was eat them to beat them. So what we wanted to do was to ensure that there was nutritional benefit from eating the fish and that there was no detrimental effects from potential toxic exposure from things such as mercury or arsenic. Again, we have participated in UE biannual conferences presenting on conch, a major seafood export, and we ensure by analyzing for local clients that they will pass the code limits as set by the EU so that they can export to the EU. Mineral composition of foods is a big part of what we do, and by doing that, we have managed to produce dietary intake tables, and this is also being published in a book that I can share the details with later if you need. So not just on the beneficial, but also on the potentially toxic. So what does the future hold? What will Prof Lalor's legacy be? Well, one of our major projects will be the installation of a multi-purpose irradiator project. So that's something that is well underway. I've already received funding. It's just a matter of the actual installation, which has been heavily affected by our COVID situation. So with the growing recognition of the importance of nuclear technology to assist national development, particularly in agriculture, medicine, industry, research and education, I put forward a proposal to house a multi-purpose gamma irradiated facility at Iceland. There will be 2 initial projects that are based on the most pressing needs. So that being the eradication of the Aedes aegypti mosquito. So just to put that in context, in 2015, it was estimated that 1.4 million persons were affected by chikungunya, with an incidence rate of 49.2%. Approximately 48% of employed persons were affected. Estimated that we lost $6.6 billion, or 0.51% of GDP. Potential 12 million man hours. This virus, along with Zika and dengue, is spread by the Aedes aegypti, as I mentioned, and we will be using this gamma irradiator to sterilize male mosquitoes, only females bite, and release them back into the environment where they will mate but produce no offspring that are viable, and thereby suppressing the population. Now, shown here on the diagram is first step is mass rearing. This is being undertaken by the Ministry of Health and is ongoing as we speak. Our role is right here, the irradiation of the males just to the right amount, not to make them unattractive to female mosquitoes, and then aerial release, mating but no offspring, thereby suppressing the population. The other project is looking at the improvement of crop production yields by improving their resistance to pests, drought and saline intrusion and other climatic changes. This will be done by irradiating plant nets and seeds, exposing them to gamma treatment and causing what the process known as mutagenesis. Now, this occurs naturally in the natural environment, but it takes about 1 every 10,000 events to produce a viable plant that will have the qualities that you need. By exposing them to gamma rays higher than background radiation at just the right amount, not at a level to damage them, we are simply speeding up what is a natural process. But it is hoped that by selecting plants that exhibit a transmittable quality that you want, like I said, either pest resistant or higher yield, you can then breed a strain that will be beneficial to the local agricultural sector. So we can also use, so in the medium to long term, this multi-purpose facility will not only allow the sustainable implementation of the 2 projects I just mentioned, it can be applied to numerous other crops and vectors, both in Jamaica and in other countries in the region. Additionally, the introduction of gamma ray technology to other aspects of agriculture, that is shelf life extension of seasonal crops, increase crop export because we can actually eradicate pests, such as those produced by the West Indian fruit fly. We can irradiate the fruit and eliminate the eggs. We can also extend this to the health sector, looking at equipment sterilization, improved skin graft technology. This could have profound effects on both sectors. So Iceland's leadership roles for small island developing states, well, we are actually heading 2 major projects now for the International Atomic Energy Agency, one regional on building capacity and sustaining national regulatory bodies. That's 8 Caribbean CARICOM countries that are also IEA members now, and one global project on the contributing to the development of small island developing states by building human and institutional capacities in nuclear sciences and technology. So a total of 19 countries across the globe, all small island developing states. And sorry to say, I'm not calling Belize and Guyana small island developing states, but they're also part of this project. With that said, I am happy to answer any questions you may have, and I hope that you didn't find it too boring. Thank you for your attention.
Oh, thank you so much, Professor Charles. It is, Professor Grant, it is actually quite amazing to see quite the diverse range of projects that you've been involved in. They're just up the road from us, and well, I don't know if anybody else did the dive, but I didn't. It's really, thank you. I am going to ask if there anyone who has any question. Anyone has no? Field it to Professor Grant.
Hi, Charles. Rob Lancashire here. I always like to hear the story from Prof about the trip to Brussels with BBC Preston at that stage, and the idea that they were able to get Maurice Foley, who was in charge of the funding for this EU project, and they caught him at a good time apparently, because he said, what else would you like, after they'd spent the day discussing funding. And apparently Bunny said, I want a reactor. And the man's face didn't drop and go berserk. He said, well, tell me a little bit more about what you're thinking of. And eventually he was able to help, despite the fact that it was EU money, and they bought a Canadian piece of equipment. And I've always loved that story.
Only Prof later.
Yeah.
Amazing. Inca, Dr. I think she's asking a question that I had. She's asking, is the information from the Stolen Beach study publicly available? Well, my added question to that, did anybody get arrested for that?
Nobody got arrested, and I am shy to implicate anybody. You know the situation that we live under. So funny enough, naturally, the sand came back up through natural action. So the beach now has sand in it again.
Okay.
So, but the fact that 500 trucks had to move through the area means you didn't really need neutron activation analysis to find out who stole it. But nonetheless, it's the world that we live in.
It is. And, of course, I mean, as you said, one doesn't want to risk one's life, in terms of getting to the bottom of some of these things. But hey, Professor Kawa, go right ahead.
Yeah, thank you very much, Winklet. Charles, thank you so much for that, summary of the great things that you have been doing at Iceland. I just wanted to add as well that the nuclear activation analysis technique has been impactful on our basic research. As you saw, nuclear activation analysis is very good for lanthanides, the rare earths, and we took advantage of that, and we were able to do some chemistry that only has were publishing at that time, looking at mixtures. If you take a mixture of lanthanides into one pot, you know, and then you examine how they are competing for coordination, et cetera, which produces quite fantastic results. And quite a number of students, you know, Marvin, his family, Alison, Max, I mean, a whole lot of, you know, my students benefited from the presence of that facility. So I want to thank you very much, you know, for extending, you know, that courtesy, you know, to us and building capacity really in these areas. And finally, just want also to add that for quite a long time, Iceland has been functioning as an atomic energy agency. Many countries have an atomic energy agency to promote the peaceful use of atoms, atomic energy, sorry. But they also have a regulator, and somehow the Iceland helped us to help Jamaica and indeed the region to meet the international obligations associated with both. And I mean, we recently took the regulatory aspect, you know, from them, but we still benefit quite a lot from training, capacity building, you know, and you know, and so on. And again, we thank you so much. And the whole aspect of bringing science to work, you have brought it alive. It is in the economic space, it is in the health space. That is very, 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 very good for science. So thank you so much. And thanks so much for this great man, Professor Gerald Lalor.
Awesome, awesome. Thank you so much, Mr. Kawa. You had anything you wanted to say, Professor Grant, before going on to Robin's question?
No, just endorsing what Prof has said. We are thankful for Prof Lalor for, well, if it wasn't for him, I would not be here, that's for sure. You know, it's down to him, and we still owe him a vote of thanks, which I think we're trying to do now, but nonetheless.
Okay. Thank you, thank you, thank you. Dr. Rattree, we see that you're famous. Your picture is on the front of this. I mean, wow.
I need to apologize for that, colleagues. I didn't intend. I didn't think Charles would have put you to that in that uncomfortable position. But thank you, Charles, for such a memorable and such a almost emotional, for me, presentation, because, you know, we go a long way back and you took us right down memory lane this morning. But I'm happy to see, you know, the things that are going on. And my question really relates to the multi-purpose irradiation project that you mentioned. And I think this is just so appropriate, because it fits right in with what Prof Lalor always used to propose, you know, where you take a tool and you use it for many different things. As he said with the nuclear reactor, as you explained. So I think he'll be very happy to see this project proceeded. Having said that, though, I want to ask you, Charles, and I see Gerald in the audience, so he will know the history of the sterile insect experience with the screwworm eradication that I don't think was perfectly successful. And I wonder if you're aware of that. I know you're aware of it, but how you plan to address some of the challenges that they at VSD, Vet Services Division, that they met when they tried to use this technique to eradicate the screwworm.
Thanks for the question, Robin. I think a lot of the failure of that project was that it wasn't driven by the entomologist. It was driven by other factors. What I intend to do here, and as you quite rightly said, is to partner with them, work with their schedule, because a lot of it, the key to sterile insect technique is timely release of the sterilized male. There's no point in doing it when the population is high. You won't have impact. These techniques work alongside the other traditional methods for population reduction, but you need to use it as like the final death nail, so to speak. So you reduce the population, and then at the right point in time, which the entomologist should drive, will tell you that now we need the big influx of these sterile males just to finally push the levels way down. So there was a lot of timing issues. So I've spoke to some of the entomologists from that project, and I've really taken heed from what they've said. But I think having the irradiator here, rather than relying on an external person providing the irradiation for you, should be able to take care of that issue. That is my strong belief, because I won't be running it from a technology side. I'm looking for the expertise, and I've seen a few questions about asking about collaboration. This is exactly what I intend to do. I'm a nuclear physicist. I am not a biologist. I am not an agriculturalist, but I understand the problems and I understand how the technique can assist, but it should be driven. I mean, I'll take care of the technology, but the other side should be driven by the experts in that field. So I think that's how we can get over that this time.
Okay, thanks for that, Charles, because I just want to wrap up by saying that that was also one of Prof. Lalor's philosophies, it's a team. Everybody brings something to the team, and therefore you get a better chance of success. You can't do everything by yourself.
Exactly.
And so I'm glad to hear that position. But what I wanted to ask you, though, and maybe Errol also, if he's in the room still, I don't know if this was a sort of barroom talk, but what I heard at one occasion, the problem with the sterile insect technique applied to the screwworm larvae is that the males that were irradiated in Mexico, I believe, and brought to Jamaica and released were not attractive to the Jamaican females. That they were not big enough or something like that. Anyway, so they did not, they were not attracted to them. So they focused on the Jamaican males who were not sterile, and therefore the problem. But I don't know if you can add any.
So, and I don't know if maybe you missed, or maybe I didn't say it loud enough, that we're actually doing our mass rearing here at the Ministry of Health. I think we're up to 1 million mosquitoes per week in a limited facility. So the very reason that you mentioned, we want the local population. We're going to mass rear them. We're not going to bring in an external male. We're breeding them ourselves.
Okay, thanks, Charles. I missed that, but thanks very much and congratulations.
Okay, thanks.
Great, thank you so much. I'm going to hand over to Professor Rees, who will field a couple more questions. And so again, thank you so much, Professor Grant, and have a wonderful day. A question, Mark. So, yes.
Sorry, go ahead, Mr. Collins. Sorry, Mark, I know your mic is open and I think you're speaking, but we're not hearing you. I'm not sure if you need to use another device.
Yeah, maybe I could make a comment, a quick comment.
Yes, go ahead, Prof. Carlo.
Yes, Professor Grant spoke about collaborations, and I wanted to emphasize as well that the Iceland and Charles and his team have a huge reputation at the international level. When you go to the International Atomic Energy Agency headquarters and you mentioned Charles Grant, people really respond admirably. And so I was thinking that we can exploit that reputation that has been built by Charles and Leila and colleagues by putting together clever projects. Anybody can put to, as Charles indicated, anybody can put together a project that can actually utilize atomic energy. And there is plenty of support from the International Atomic Energy Agency and other areas. They're anxious to support us. So I would encourage all the young people in doing their research and so on to try and figure out how they can weave in any area of research. How can you weave in atomic energy and garner some support that is desperately needed?
Totally agree, Prof. And we are open to collaboration, as I said earlier. So we would welcome such approaches.
All right, Professor Grant, there is a message from Ian Thompson. I know you touched on it, but and he was asking specifically about Jamaica's roots and he says the increased runoff, sorry, from arable lands may tend to concentrate heavy metals in our soils, and these turn up in our food at higher levels.
Mm-hmm. I had answered him directly.
Oh, sorry. Okay.
But not a problem. I say yes, we do have, as I said, we developed nutritional food tables as well, but we do have significant information on tubers across the island that in different like different soil concentrations for particular heavy metals, cadmium being one of interest, and of course cadmium and arsenic, chromium, and so on and so on. So yes, the answer is we do, and we could look at how we could collaborate on that for sure.
Okay.
And I agree, the runoff could be a huge issue.
Okay, I'm just looking, see if there are any other hands. Robin had asked a question, and he described it as bar talk, and I'm going to ask a similar one. And I'm not really up on this, but the issue with the cadmium in the soils, initially when the news, I don't want to say came out, because I think it was whispered across the campus. There was the wonder, why are we not, we're all eating food from, say, St. Elizabeth, etc. Why is it that we're not all dropping dead? To put it bluntly.
Yeah, I get it. I think partially a lot of the scare, not that it's unfounded, but the limits that were set were based from the Itai study in Japan. It was a number of persons, octogenarians, that were subsistent farmers, had multiple children, had a number of deficiencies. They lived near a cadmium mine or a cadmium mining area. The waste runoff came into the rice paddies. The levels of cadmium in the rice that they ate was extremely elevated. But I think the impact that it had on that population was extreme. I don't know if it would be so on a normally healthy population or a relatively healthy population or a population that is not deficient in everything almost, if the impact would have been quite so high. So I think the levels that they set, saying that, boy, you should have almost, I'm sure you shouldn't have any cadmium in your body. But if you are severely deficient in almost every needed trace element in your body, the slightest element that looks like something useful, because it's an analog of zinc, cadmium, your body may grab onto it. And so I suspect the impact in that population was extremely large. Like I said, cadmium at any level in your body is never really acceptable, but I suspect the scare to say, well, it's going to kill you instantly, stems from that, in my belief. This is my opinion on it. The fact that, like you say, people have been living on that soil for the last 400 years, yet still some of the oldest people in Jamaica live on some of the highest levels in northern Manchester. So there is that question hounds me as well, but that's my take on it. I think the original study population was not truly representative of what a normal population looks like.
All right, thank you. I know time is running on, but I see two more hands. Errol Dakin, and apparently Ian Thompson has a question as well. So Mr. Dakin, could you go ahead pretty quickly, and then Dr. Thompson?
Yeah, man, sure. Thanks, Professor Charles. That was a great presentation. I have a question for you, but I wanted to clear up something with Dr. Rattray with respect to the schoolworm program. We had a local entomologist from the university working on that program, and I am not sure why that program actually didn't work, but what they said was the compatibility of the flies, the local flies and the artificial flies, why it didn't work. And I'm not sure if there's still funding available for that particular project, because that was a hugely funded project. So I'm really not sure the status of that project now. But I want to ask Professor Charles one question. Is there any study that was done with respect to the interaction between the different elements in the soil? Because I know that from a study that we did with copper, we know that elements like molybdenum and sulfate in the soil affect the absorption of copper. So I'm wondering if other elements in the soil would affect the absorption of things like cadmium and so forth. Was any study like that done by Iceland?
Yeah, we did take a look at a way of trying to reduce the uptake of cadmium into tubers by liming the soil. So things like changing the pH and so on like that, we know will have effects. I don't think we really looked at the addition of other metals to see if it would inhibit uptake. So we haven't done studies like that, but we did try to change the pH of the soil to see if that had an impact. But again, as I mentioned, with living things, the variables are so many that unless we produce it year in, year out, you're not really quite sure as the impact that the steps that you're taking are having. So it's a difficult study. But no, I don't believe that we've done anything with metal and metal to see how that affected uptake.
Okay, thanks.
Mm-hmm. Right. And Dr. Thompson, you have the last word.
Okay. Thanks for that interesting and informative presentation, Prof. Grant. I'm interested in this matter of uptake of heavy metals in roots and tubers because we're involved in a project where we were processing roots and tubers. And to my surprise, when we tried to, well, we had a request from a European customer. And of course, we sent them a sample. And to my surprise, the levels exceeded their limits. Further work suggested that over time, in the area that we were growing these roots and tubers, we've had significant concentration of these heavy metals. And yes, I think a lot of, well, we read some work suggesting that, strategies to avoid this take-up are available. And you mentioned one of them, liming. But the fact is that this is a real problem. I'm not sure how we have gotten away with, still exporting some of these food products, and they have not, been flagged for heavy metal content.
It's been amazing to us too. I think Robin can attest to this as well too. Robin was here at the time. We had like a kind of a break the glass emergency situation plan. If anyone ever red flagged us, because we did report extensively to the Ministry of Agriculture, and it was just kind of pushed away, for want of a better word. So we understand. We almost can tell you where you can and cannot plant certain crops. I mean, as I indicated in the yam chart against soil cadmium, you can tell at what point you're going to exceed certain limits. I mean, it's not always definitive, like I said, because of the complexity of living things and how they uptake. But there are points where you can say definitely do not plant in soil above this concentration. So we have a pretty good understanding of that. I would be happy to share with you anything we know in terms of where you're planting or where we could recommend that you plant. But yes, I'm sure the penny will drop one day, and I hope it doesn't, but I only think it's a matter of time before someone, for whatever reason, decides to take a look, and that could be an issue.
Yeah, so it's very concerning, primarily because these crops affect such a wide cross section of the, these rural communities, which depend on these crops for income, and as a result,
yeah, we have been very worried, and I can be just straightforward here. It's part of the reason why we haven't published largely on the cadmium in certain products. I don't think none of us want to be associated with the death of an industry.
Right, Dr. Rattray, I think you had a comment to make on this.
Yeah, thanks, Prof. Just 5 seconds. Sorry to barge in, but I had to add this anecdote because it's a political situation also, right? Basically, I can say this now because I'm no longer at Iceland, but it's a political situation. Charles can't say it.
Yes, I can.
But I remember sitting beside a Minister of Agriculture who will remain nameless, pointing out the cadmium situation. This is at a meeting discussing the thing, and he was quite blunt. He said to me, if there's cadmium in the yam in Manchester, that's okay, but you are going to go down there and tell them they can't plant yam, not me. And that was the end of the story. So politically there is not the will, I think, to address the situation. So we just sort of dancing through the raindrops, and as Charles said, the penny might drop one day soon. Okay, that's it from me.
Right. Okay. Well, I think we really need to bring this to a close. But Professor Grant, Charles, thank you very much for speaking to us, taking time out from your very busy schedule, and also providing a talk that all of us could understand, and just for filling us in on the quality work that is occurring at Iceland. Thank you for continuing Prof. Lalor's legacy. I think that you're a great successor to him.
Thank you very much for that, Prof. I appreciate it. Always good to hear.
Okay, all right. Take care, everyone. So until next week, keep safe.
Thank you all for inviting me. Take care. Bye.